Let us develop the concept, try to develop a concept where we can talk about that why some of the nucleuses are stable and why others are unstable. And that's the target of this video. And to begin with, to start with, the very first thing with which we would like to start here is the Einstein's mass energy equivalence. And what we have for that is E is equal to mc square. So the symbols have their usual meanings. E refers to energy, m is the mass, and c is the speed of light. Now, to write down the total energy is basically equal to the it's equal to the sum of this rest mass energy and kinetic energy. So if I have to write down that total energy, that will be the rest mass energy plus the kinetic energy. Now for this E, I have mc square. So I can immediately use mc square here is equal to m naught c square plus k. And this equation basically tells us that the rest mass energy can be, this rest mass energy can be converted into other forms of energy. And this equation merges two principles. It has two principles in it. One is the law of conservation of energy, and another is law of conservation of mass. Law of conservation of E for energy, and law of conservation of mass. And these two things are basically incorporated into a single law of conservation of total relativistic energy. So this equation is basically incorporated in it the conservation of mass and the conservation of energy. And if we have to draft it into a single form, then this equation is basically the conservation of total relativistic energy. So conservation of total relativistic energy. So we can have kinetic energy from here. So we can have kinetic energy that K will be mc square minus m naught c square. So this kinetic energy will be m minus m naught times c square. So this kinetic energy is it is delta m c square. Now this delta m is we have this as change in mass, so we can assign this delta m as mass defect. And what we see from here is that the kinetic energy of the particle is change in mass. It is change in mass times the square of speed of light. And at this point, if we want to get an idea about the energy that can be that we can have when there is a change in mass. So if I take an example at this point, say for example, I have a mass of 1 mg, and speed of light is 3 to 10 to the power of 8 meter per second. So how much energy I would expect from this small mass will be given by mc square, and that will be 10 to the power of minus 6 kilograms times 9 into 10 to the power of 16 joules. So certainly we are getting here 9 into 10 to the power of 10 joules. and we can convert this 1 milligram of mass. The energy that we can have is 9 into 10 to the power 10 joules, and I can convert it into electron volts by dividing it by 1.6 10 to the power of minus 19. And here we will get the value nearly 6 into 10 to the power of 29 electron volts. And we can have an understanding that how tremendous the mass can give energy if you are taking a small mass of 1 milligram. So we can expect a huge energy in mega electron volts here. So we can have 6 times 10 to the power of 6 times 10 to the power of 23. Then we will have 6 times 10 to the power of 23 of mega electron volts of energy that we can have from here. Now, what is the intuition here is that this change in mass can be a consequence of tremendous amount of energy. Now, now the mass that we have, the delta m, this is the mass defect. Now, we want to calculate this mass defect for the nucleus in terms of its parameters, in terms of its nuclides or nuclear species that we have there. So this delta m is basically the difference between the mass of the constituent nucleons of a nucleus in free state and the mass of the nucleus. So the mass of the separate nucleons and mass of the nucleus, subtract the two, what we'll get is the mass defect. And this mass defect is symbolized as delta m. Now, going into the domain of nucleus, now when a nucleus of an atom is formed, let's assume that we form a nucleus by bringing the protons and neutrons together. So when we do that, the mass of the nucleus so formed, we'll get a nucleus out of it. We have protons and neutrons and protons and neutrons. And the mass of the nucleus that's so formed is less than the sum of the masses of these constituent particles, right? So the difference of the mass between the nucleus and the nucleons, that difference is called as mass defect. And to have a symbolic presentation of this mass defect, I assume a nucleus, and this nucleus has a mass m, and it has z number of protons, so it will have a minus z number of neutrons. That's the case. And let me assume that this mn is the mass of each neutron, mass of each neutron, and mp is the mass of each proton. All right. As I stated, we have to do the external work to bring all of these nucleons together to form a nucleus, and the reason is the work that we have done here to bring all of these nucleons, and this gives rise to the mass defect. So what we have here is we have the mass of each neutron as mn, the mass of each proton as mp, and we have z as atomic number, and a minus z will give us the number of neutrons. So atomic number here automatically means number of protons. So to say that what will be the mass of z protons? What will be the mass of z protons? Because there are only z number of protons, that will be z mp. And similarly, the mass of a minus z neutrons, that will be mn times A minus Z. So sum of the masses of the protons and neutrons. So if I write the total mass here, the total mass, and what will be that? The total mass of protons and neutrons. That will be mpz or zmp plus mn times A minus Z. All right. And now, if I have to write down the mass defect, because I have chosen m as the mass of the nucleus, so what I will have here is the mass defect. So this is the mass of the constituent particles in the nucleus, and this is the mass of the original nucleus. So here I will have delta m, I will have mass defect. And how would I write that mass defect is simply Z of mass of protons plus A minus Z of mass of neutrons times minus the mass of the original nucleus. Now this mass defect that we have here, this can be measured in terms of atomic mass units, or it can be measured in terms of kilograms. So to move from here, so this equation is giving me the mass defect. So now I can I can define the term. I would like to define the term nuclear binding energy. Nuclear binding energy. Okay, so what is this nuclear binding energy? Is in simple words, we can understand it that it's the total energy that's required to disintegrate a nucleus into its constituent particles or nucleons, and this energy is referred as nuclear binding energy. Now, binding energy is basically what I said. It's basically the energy required to hold the nucleons in the nucleus. When nucleons form a nucleus, the mass of the nucleus is less than the sum of the masses of the nucleons. So there is certainly the decrease in the mass of the nucleons, and this decrease in the mass is an indicator of mass defect. And what's happening to this decrease in mass of the nucleons? This is the mass that's converted into the energy in accordance with the equation that we have. Now I will call this EB, the binding energy of the nucleus, that is delta mc square. That should be the case. And I can use here for delta m, and I can have the binding energy. So binding energy can be written as ZmP plus A minus ZmN. Then we will have minus m, and then we will have c square. That's the case, and we have already converted. We can express this binding energy. We can express this binding energy in terms of joules, and then we can have this binding energy in terms of electron volts. Now this is my mass defect, and this is the speed of the light, and this is giving me the measure of what? It's giving me the measure of the binding energy. So to write down this equation of binding energy in terms of atomic mass units, so this EB will be simply ZmP plus A minus ZmN minus M atomic mass in terms of atomic mass units. And we know that one atomic mass unit, we have converted that using the equation, and this one atomic mass unit is nearly 931 mega electron volts. So if that's the case, I can write down this binding energy of the nucleus as the multiplication of mass defect times 931 mega electron volts for the nucleus that has been considered here. And this equation is giving me the binding energy of the nucleus. And now, if I divide this equation by the number of nucleons, if I divide this equation by the number of nucleons, what's the number of nucleons? That is A. So, so if I divide this EB by mass number, so what I'll have is delta M times 931 mega electron volts by mass number. Now this is called as binding energy per nucleon. So this is nothing by binding energy per nucleon. Okay, so I would like to call it EBN. So this binding energy per nucleon is delta M times 931 mega electron volts by the mass number. Now, this binding energy per nucleon, it basically determines the stability of the nucleus. It talks about the stability. And if I'm saying stability, it's also giving me the idea of instability of the nucleus. So there can be stable nucleuses, there can be unstable nucleuses. And the nucleuses who will have large binding energy per nucleon, they'll be preferably stable nucleuses, and the nucleuses who have less binding energy per nucleon, they will be unstable nucleuses. So to say is that this is the stability of the nucleus is basically it is proportional to the binding energy per nucleon. Now, if the binding energy per nucleon of the nucleus is less, that I'm trying to repeat is then the nucleus is stable, and otherwise nucleus is unstable. So what we will try to do here is to if we draw this this binding energy per nucleon curve, it goes like this. Then it comes down, then it goes up, then it comes down, then it goes up, then it comes down, and then it goes, and then it comes down like this. And this is mass number. This is mass number. And this is binding energy per nucleon, EBN. And here we have hydrogen, we have lithium, we have oxygen, and we have nitrogen, and these are all the nucleuses that are here on this binding energy per nucleon, and then here is molybdenum, then here it is nearly it is indium, and then we have tungsten, and then we have uranium, and this is we can check it from anywhere. This is the binding energy per nucleon curve to get the rough idea about the nucleuses that we have interpreted here in this graph. Now, what we see here is that the variation of binding energy per nucleon with mass number, and we can see for large number of nucleuses that we have here, this binding energy per nucleon curve. Now, what is so important about this is that the average binding energy per nucleon for mass numbers who have mass number less than 3, their average binding energy per nucleon is small, and some nuclei with the mass number whose mass numbers are between 3 to 20, they have large binding energy. They have large binding energy per nucleon than their neighboring nuclei. Now, for example, if I take an example of helium 4 2 or beryllium 8 4 and carbon 12 and 6, oxygen 16 and 8, and neon 20 and with its atomic number 10, they have greater binding energy per nucleon than their neighbors. So the nuclei, these nuclei are more stable. They are more stable nucleuses. And then if we go for the mass numbers between 30 to 62, so this is my axis. Okay, so here I can dip things in terms of the nearly 25, then 50, then 75, and then 100, then 125, then 150, 175, and so on and so forth. So when the nucleuses that are falling between 30 and 62, their binding energy per nucleon increases gradually and attains a maximum value of 8.8 mega electron volts. So we have this binding energy, and this binding energy is in mega electron volts as we have calculated it. So to say, and the maximum value for this binding energy is 8.8 when we move from the mass number 30 to 62. And this is why what we have, iron and nickel, they are stable nucleuses because their binding energy per nucleon is extremely large. Right now, for nucleuses whose mass number is greater than 62, binding energy per nucleon gradually it goes on decreasing. And for uranium, if I take for uranium 238, if I take uranium 238, it is one of the heaviest natural elements. The value of binding energy per nucleon, it drops down to 7.5 mega electron volts. So these are the outcomes of this binding energy curve that correlates binding energy per nucleon with respect to the mass number, and these were some of the important observations of this binding energy curve. Now, if I have to conclude this binding energy, now what would I like to say is that this graph is giving me the rough idea about. I am giving you the rough idea here that the intermediate nuclei have large value of binding energy per nucleon, so they are more stable, which are intermediate nucleuses here, and the binding energy per nucleon has low value for both lighter elements and very heavy elements. So the lighter elements and the heavy elements, they are unstable because their binding energy per nucleon is less. Now the point is, when we have a heavy nucleus, what happens? It splits. We have a heavy nucleus. It splits up into lighter nuclei. Then binding energy per nucleon of the lighter nuclei is certainly more than that of the original heavy nucleus that splits into the daughter nucleuses. So what it means is that the nucleons of lighter nuclei are more tightly bound. Thus, energy is released in this process, and we infer that this is the process of fission. This is what is called nuclear fission. And when we have two very light nucleuses, the reverse of it, and of whose mass numbers are less than that, less or equal to 10, when they combine to form a relatively heavy nucleus, what happens? Then the binding energy per nucleon of the heavy nucleus, the one which is fused here by these lighter nucleuses, becomes more than that of the lighter nucleuses. Okay, so in other words, I should say here that the nucleons of the fused heavy nucleus are tightly bound, the reverse of what I talked about, the fission. Thus the energy is released in this process, and this process becomes the basis of what is called as nuclear fusion. So with this, I would like to stop and tell you goodbye. Have a good time. That's it.